Picture looking up at the night sky, seeing the familiar pinpricks of stars, the hazy glow of distant galaxies, but there's something else, something invisible to your eyes, stretching across the entire universe. A whisper of ultraviolet light, faint yet everywhere, like a secret written in the darkness itself. This is the Cosmic Ultraviolet Background, or CUVB for short, an enigmatic glow that has puzzled astronomers for decades. It's not coming from any one star or galaxy, but seems to seep from the fabric of space, a cosmic hum we're only just beginning to understand. What makes this glow so mysterious? Imagine it like trying to solve a jigsaw puzzle where half the pieces are missing, and the ones we have keep changing shape. The CUVB shouldn't exist in the way we observe it. The universe is vast, but it's also mostly empty, so where is all this ultraviolet light coming from? Some of it might be leftovers from the birth of the first stars, echoes of a time when the cosmos was young and violent. Other parts could be clues to phenomena we haven't even discovered yet, hidden galaxies, rogue particles, or forces we can't yet measure. Every time scientists think they've cracked the code, the CUVB throws another curveball, refusing to give up its secrets easily. That's where the adventure begins. In this video, we're diving into 25 of the most baffling mysteries tied to this cosmic ultraviolet background, questions that stretch our understanding of the universe to its limits. Why does the CUVB appear brighter in some directions than others? Could it be a sign of dark matter's invisible fingerprints, or is it pointing us toward an entirely new layer of physics, something beyond our current theories? Buckle up, because this isn't just a story about light in space. It's a detective story, a treasure hunt across the cosmos, and you're right there in the thick of it. By the time we're done, you'll never look at the night sky the same way again. The first and perhaps biggest mystery of the cosmic ultraviolet background is its very existence. Where does all this light come from? If you could see ultraviolet with your own eyes, the entire sky would shimmer with it, a faint but persistent glow stretching across space. The problem is, when astronomers tally up all the known sources, quasars blasting out radiation, young galaxies packed with hot stars, even the diffuse gas between galaxies, the numbers just don't add up. There's too much ultraviolet light, and it's coming from places it shouldn't be. Take quasars, for example. These supermassive black holes at the centers of galaxies devour matter and spit out incredible amounts of energy, including ultraviolet radiation. They're like cosmic lighthouses shining across billions of light years. But here's the catch: quasars are rare. There simply aren't enough of them to account for the sheer volume of ultraviolet light we detect. Then there's star-forming galaxies, where massive stars burn bright and hot, bathing their surroundings in ultraviolet. These should be prime suspects, yet when scientists map their distribution, huge patches of the CUVB remain unexplained. The light appears where no known galaxies exist, as if the universe itself is leaking ultraviolet. That's where things get truly fascinating. Some theories go beyond conventional astrophysics, suggesting exotic possibilities like decaying dark matter. Imagine invisible particles, remnants from the early universe, slowly disintegrating and releasing energy, including ultraviolet photons. It's a wild idea, but one that could explain why the glow seems to come from nowhere and everywhere at once. Others speculate about hidden populations of ultra-faint galaxies, too dim for our telescopes to spot directly, yet collectively bright enough to paint the cosmos with this eerie light. To untangle this puzzle, astronomers rely on instruments like the Hubble Space Telescope, which acts like a cosmic detective, filtering out the noise to isolate the CUVB faint signal. Even then, every answer brings new questions. Why does the glow vary in intensity across different regions of space? Could multiple sources be at play, each contributing in ways we don't yet understand? The more we learn, the clearer it becomes. The origin of the cosmic ultraviolet background isn't just one mystery. It's a web of them, pulling us deeper into the unknown. The mystery deepens when we realize just how much ultraviolet light is unaccounted for, like turning on every light in a city and still finding dark patches no one can explain. This is the missing sources problem. The cosmic ultraviolet background glows far brighter than the combined output of all known stars, galaxies, and quasars. It's as if the universe left half its lights on, but we can't find the switches. Take a moment to picture how astronomers calculate this. They add up every confirmed ultraviolet emitter, the blazing cores of active galaxies, clusters of newborn stars, even the faint glow from intergalactic gas. But when they compare that total to the CUVB actual brightness, the numbers fall short by a staggering margin. Some estimates suggest up to half the ultraviolet light in the cosmos has no identifiable origin. That's not just a rounding error, it's a gaping hole in our understanding of how energy flows through the universe. One leading hypothesis points to galaxies so dim and distant, they've slipped past our telescopes undetected. Think of them like cosmic fireflies, individually too faint to spot, but collectively capable of bathing the universe in ultraviolet. Recent simulations support this idea, predicting vast populations of ultra-faint dwarf galaxies lurking in the cosmic shadows. If they exist, their combined light could solve part of the puzzle. The challenge: these galaxies would be orders of magnitude dimmer than anything we've observed before, pushing our instruments to their limits. Then there's the darker possibility, literally. Some researchers argue the missing energy might come from dark matter, the invisible scaffolding of the cosmos. Certain theories suggest dark matter particles could decay over eons, releasing ultraviolet photons as they break apart. It's a tantalizing thought. The glow we see might be the ghostly aftermath of particles disintegrating in the void. While no direct evidence confirms this yet, it's a reminder that the CUVB could be more than just light. It might be a message from the universe's hidden architecture. Between these two extremes lies a spectrum of other explanations. Could scattered stars flung from galaxies during cosmic collisions be contributing? Might there be exotic objects like rogue black holes or primordial remnants radiating ultraviolet in ways we haven't predicted? Every hypothesis forces us to rethink what we know about the universe's energy budget. The missing sources problem isn't just about finding more lights, it's about discovering entirely new kinds of switches. Imagine trying to see through a dense fog, the kind that blurs streetlights into hazy halos and turns familiar landmarks into ghostly outlines. Now picture that fog stretching across the entire universe, not made of water droplets, but of scorching hot gas floating between galaxies. This intergalactic medium isn't just empty space, it's a sprawling ocean of atoms, so thin you could fly through a cubic foot of it and barely touch a single particle, yet so vast it weaves a cosmic veil that twists how we see ultraviolet light. Here's the twist: this gas doesn't just block ultraviolet radiation, it transforms it. When a photon of UV light from a distant quasar or galaxy slams into a hydrogen atom in the intergalactic medium, it gets absorbed like a sponge soaking up water. But that energy doesn't vanish. The atom re-emits the light, often at slightly different wavelengths, scattering it in unpredictable directions. The result: a kind of celestial smog that smears the ultraviolet background, making precise measurements a nightmare. Astronomers call this the Lyman alpha forest, not because there are actual trees, but because the absorption lines it creates in spectra look like a dense thicket of spikes. Mapping this fog is like trying to chart a hurricane by watching how it distorts candle flames. The gas isn't evenly distributed, it clumps into filaments and bubbles, remnants of the universe's large-scale structure. Some regions are nearly transparent, while others absorb so fiercely they cast shadows across billions of light years. To complicate things further, this gas isn't static. It's in constant motion, stirred by the gravitational pull of dark matter and the explosive energy of supernova. Each patch of intergalactic medium has its own temperature, density, and chemical fingerprint, meaning it interacts with ultraviolet light in subtly different ways. This chaos has a direct impact on CUVB measurements. If we underestimate the gas's absorption, we might mistake dimmed light for missing sources, overcorrect for it, and suddenly the background seems fainter than it truly is. It's a Goldilocks problem. Getting the balance just right requires instruments sensitive enough to detect faint UV signals while filtering out the gas's distorting effects. Missions like the Cosmic Origin spectrograph on Hubble have made strides analyzing quasar light that's passed through these cosmic filters, but even with cutting-edge tools, uncertainties linger. Could pockets of ultra-hot gas, undetectable by current methods, be skewing the data? Might there be exotic particles embedded in the intergalactic medium, altering how light travels through it? The intergalactic gas isn't just an obstacle, it's a clue. Its very existence hints at the universe's violent youth, when galaxies were first forming and radiation ripped electrons from atoms in a process called reionization. Some of that primordial energy might still echo in the CUVB, tangled up with newer light. Untangling this mess could reveal not just where the ultraviolet background comes from, but how the cosmos evolved from a dark, featureless void into the glittering web we see today. The fog isn't just obscuring our view. It's hiding stories written in ultraviolet, waiting to be decoded. Long before stars flickered to life, before galaxies spiraled into existence, the universe was cloaked in darkness, a silent, featureless expanse that astronomers call the cosmic dark ages. This shadowy era lasted for hundreds of millions of years after the Big Bang, a time when the cosmos was too young for starlight, filled instead with a thick fog of neutral hydrogen gas. But here's where things get intriguing. Could remnants of that primordial darkness still linger in the cosmic ultraviolet background we see today? The connection hinges on reionization, the universe's great awakening. When the first stars and galaxies finally ignited, their fierce ultraviolet radiation blasted through the cosmic fog, stripping electrons from atoms and transforming the opaque hydrogen into transparent plasma. It was like a curtain lifting on the cosmos, but the process wasn't instantaneous or uniform. Some pockets of gas resisted longer, while others cleared quickly, leaving behind a patchwork of light and shadow. The energy from that tumultuous transition had to go somewhere, and some theorists propose it might still echo in the CUVB, a faint afterglow from the universe's violent adolescence. Detecting that echo, though, is like trying to hear a whisper in a hurricane. The ultraviolet light from reionization would have stretched over billions of years, its wavelengths redshifted and diluted by the expanding universe. Yet subtle clues might remain. For example, if the CUVB contains unexpected patterns, specific wavelengths, or intensity fluctuations, they could be fingerprints of those first stars, relics of an era we've never directly observed. Simulations suggest these early stars weren't like the ones we know today. They were monsters, hundreds of times more massive and blazing with ultraviolet fury. Their deaths in supernova would have scattered heavy elements and radiation, potentially seeding the background we now detect. But the challenge is untangling that ancient light from everything that came after. It's like sifting through layers of paint on a centuries-old mural, trying to isolate the original brushstrokes. One promising approach involves studying the CUVB spectrum with extreme precision, hunting for irregularities that don't match modern sources. Another looks at the background's polarization, the direction its light waves vibrate, which could preserve information about the chaotic environment of the Dark Ages. Even the way the CUVB intensity varies across the sky might hold answers. If certain patches of the glow align with regions where reionization happened last, it could hint at a direct lineage. The stakes are high. If we can decode this connection, the cosmic ultraviolet background becomes more than just a modern mystery. It's a time capsule carrying secrets from the universe's deepest past. It might reveal how those first stars formed, how quickly reionization unfolded, even what the cosmos was like before light broke through the darkness. Every photon could be a messenger from an era we've only imagined, a bridge between the universe we see and the shadowy void from which it emerged. If the cosmic ultraviolet background were a blanket, it wouldn't be smooth, it'd be lumpy, torn in places, with threads bunched up in unexpected ways. This is the anisotropy puzzle. The CUVB isn't evenly spread across the sky. Some regions blaze brighter, others fade into near darkness, and these variations aren't random. They're cosmic breadcrumbs pointing to hidden structures woven into the fabric of the universe. Take the clumps first. Telescopes have spotted patches where ultraviolet light is noticeably more intense, as if someone turned up the brightness in specific corners of space. At first glance, you might assume these are just dense clusters of galaxies, their stars pumping out extra UV radiation. But when astronomers tally up the visible matter in these areas, the numbers don't always match. Some bright patches float where there's surprisingly little galactic activity, like a spotlight shining on an empty stage. Could these be traces of invisible cosmic scaffolding, filaments of dark matter funneling energy in ways we don't yet understand? Or perhaps they're echoes of ancient quasar outbursts, their light lingering long after the quasars themselves burned out. Then there are the void's expanses where the ultraviolet glow dips sharply, creating shadowy gaps in the cosmic tapestry. These aren't just empty spaces, they're active players in the universe's structure. Gas in these regions might be cooler or more diffuse, absorbing UV light before it reaches us. Or they could mark the aftermath of colossal collisions, where shock waves from merging galaxy clusters swept the area clean of energetic particles. Some voids align eerily with known cosmic landmarks, like the Milky Way's own local void, raising questions about whether our solar system's neighborhood is subtly shaping what we see, or if we're caught in a blind spot, missing key pieces of the puzzle. Direction adds another layer of intrigue. The CUVB brightness shifts depending on where you look, as if the universe has a preferred axis. One theory suggests this could reflect the large-scale flow of matter, rivers of galaxies drifting toward unseen gravitational pulls, their motion imprinting patterns on the ultraviolet light. Another possibility involves the remnants of the universe's earliest moments. Quantum fluctuations from the Big Bang, stretched to cosmic scales, might have seeded these directional quirks before stars even formed. What makes these variations so valuable is that they're not just irregularities, they're maps. By decoding them, we might trace the invisible skeleton of the cosmos, finding clusters of dark matter or relics of primordial energy. Missions like NASA's upcoming UVEX telescope aim to chart these fluctuations with unprecedented precision, turning the CUVB patchy glow into a guidebook for the universe's hidden architecture. Every lump, every void, every directional whisper could be a clue, not just to where the light comes from, but to how the cosmos organizes itself on scales we're only beginning to grasp. The universe wasn't always this bright. Billions of years ago, before galaxies filled the darkness, space was a sea of neutral hydrogen so dense it swallowed light whole. Then came reionization, the cosmos' great awakening, when the first stars and galaxies ignited, their fierce ultraviolet radiation blasting through that primordial fog. That transformative epoch didn't just light up the universe, it left behind fingerprints we might still see in the cosmic ultraviolet background today. Think of reionization like ice melting across a frozen lake. It didn't happen all at once. The first massive stars, born in pockets of collapsing gas, burned hot and fast, their UV radiation carving bubbles of ionized hydrogen around them. Over hundreds of millions of years, these bubbles grew and merged until the entire cosmic lake had thawed. But here's where the CUVB comes in. Some of that ancient UV light, stretched and diluted by the expanding universe, could still be weaving through space today. It's the faintest echo of those first fires, and if we can isolate it, we'd hold a direct line to the universe's infancy. The challenge, separating that primordial whisper from the cacophony of newer light. Imagine trying to pick out a single violin in a symphony playing at the bottom of the ocean. One clue lies in the specific wavelength of light those early stars emitted. Unlike modern stars, which often form in metal-rich environments, the first stars were made of pure hydrogen and helium, a difference that would have shaped their UV signatures. If the CUVB contains unexpected spikes at certain wavelengths, they could be the smoking gun of reionization. Yet there's heated debate. Some argue the background's current structure is too smooth to carry relics from such a chaotic era. Others point to peculiar fluctuations in the CUVB intensity, patches too large to explain with today's galaxies as potential remnants of those early ionizing bubbles. Simulations suggest that if even a fraction of the first star's energy survived, their collective glow would create a subtle but detectable pattern in the ultraviolet background. The stakes couldn't be higher. If the CUVB truly holds these echoes, it's not just about solving a cosmic mystery, it's about rewriting our origin story. We could learn how quickly those first stars formed, whether early galaxies were efficient ionizers, even how dark matter guided the whole process. Every photon might carry answers to questions we haven't thought to ask yet, turning the cosmic ultraviolet background into the universe's oldest diary, one we're just beginning to read. Tiny, dim, and often overlooked dwarf galaxies might seem like cosmic afterthoughts next to their brilliant spiral and elliptical cousins. But what if these faint smudges of stars hold the key to unraveling the cosmic ultraviolet background's biggest mystery? With their sheer numbers and unique star-forming habits, dwarf galaxies could be the universe's best-kept secret, quietly flooding space with UV light we've been struggling to account for. Let's put their potential into perspective. While a single dwarf galaxy might emit only a trickle of ultraviolet compared to the Milky Way, their population is staggering. Current estimates suggest dwarf galaxies could outnumber regular galaxies by a factor of 100 to 1, like comparing a handful of lighthouses to a swarm of fireflies. Collectively, their output could be enormous, especially since many dwarfs are cosmic overachievers when it comes to birthing new stars. Unlike larger galaxies, where star formation is more sedate, dwarfs often experience ferocious bursts of activity, creating hot, massive stars that blaze with ultraviolet light before dying young in supernova. These fleeting but intense episodes could make them disproportionate contributors to the CUVB, like tiny sparklers that burn out quickly but outshine larger, steadier flames. The challenge lies in proving it. Most dwarf galaxies are so faint and diffuse they evade detection, especially at the far edges of the observable universe where their light is stretched and dimmed by cosmic expansion. Even our most powerful telescopes struggle to spot them beyond our galactic neighborhood, but recent advances are peeling back the veil. Ultra-deep surveys like Hubble's frontier fields have revealed populations of ultra-faint dwarfs clinging to larger galaxies like shadows, some so tenuous they contain fewer stars than a globular cluster yet stretch across thousands of light years. Simulations suggest there could be entire legions of these ghosts lurking in the darkness, their combined UV output weaving through the cosmic background like invisible threads. Yet skeptics point to a glaring inconsistency. If faint dwarfs are the missing UV sources, why doesn't their predicted distribution match the CUVB observed patterns? Some regions of the sky show ultraviolet excess where no dwarf galaxies are seen, while others rich in dwarfs don't glow as expected. This mismatch has led to wilder theories. Perhaps some dwarfs are shrouded in thick dust, muting their visible light while their UV escapes. Or maybe their star formation operates differently in the early universe, producing more UV per star than models predict. The search for answers is driving next-generation missions. NASA's upcoming Nancy Grace Roman Space Telescope, with its wide-field infrared vision, could spot dwarfs currently lost in the glare of brighter galaxies. Meanwhile, spectrographs are hunting for the chemical fingerprints of dwarf-like star formation in the CUVB light. If the pieces fit, these diminutive galaxies might solve more than just the ultraviolet puzzle. They could rewrite our understanding of how small-scale structures shape the cosmos. After all, in a universe where the tiniest things often hold the biggest surprises, it'd be fitting if the CUVB secret was hiding in plain sight all along, not in the universe's grand cathedrals, but in its humblest chapels. Dark matter doesn't just hide in the shadows. It might be painting the cosmos with ultraviolet light. That's the bold claim at the heart of this mystery, where the invisible scaffolding of the universe could double as an unlikely artist. We've long known dark matter outweighs normal matter 5 to 1. Its gravitational pull shaping galaxies and bending light. But what if it's also quietly contributing to the cosmic ultraviolet background? The idea hinges on a radical possibility that dark matter particles, after billions of years, might decay or collide, releasing energy including UV photons as they vanish into the cosmic void. Think of it like radioactive decay, but on a universal scale. Certain theoretical models suggest dark matter could consist of weakly interacting massive particles, or WIMP, which occasionally annihilate when they meet their antimatter counterparts. Others propose sterile neutrinos, ghostly particles that might disintegrate over time, shedding ultraviolet light as they go. If either scenario is true, the CUVB unexplained glow could be the faint afterglow of dark matter's slow unraveling, a cosmic farewell note written in UV. Evidence, though, is maddeningly indirect. Some researchers point to oddities like the Milky Way's galactic center, where an excess of gamma rays once sparked speculation about dark matter annihilation. While that signal turned out to have other explanations, similar anomalies in UV maps keep the hypothesis alive. For instance, certain patches of the cosmic ultraviolet background show intensities that don't align with known galaxies or quasars, regions where dark matter's subtle glow might fill the gap. The challenge is separating this hypothetical signal from the noise of ordinary astrophysical sources, like rogue stars or intergalactic gas. Critics argue the math doesn't quite add up. If dark matter were decaying uniformly, the CUVB brightness should correlate more precisely with the distribution of mass in the universe. Instead, we see mismatches, pockets of UV light floating where dark matter density is low, and vice versa. Then there's the energy problem. The amount of ultraviolet light produced would require dark matter to decay at a rate that might conflict with other cosmological observations, like the cosmic microwave background. Yet the allure persists because the implications are staggering. Confirming a dark matter link wouldn't just solve the CUVB puzzle, it'd crack open dark matter's identity. The wavelength of emitted UV photons could reveal the particle's mass. Their distribution might map the unseen structure of the cosmos. Experiments like the upcoming Louvre Space Telescope could hunt for telltale patterns in the background spectrum, while particle colliders on Earth race to recreate dark matter in labs. Until then, this remains one of astrophysics' most tantalizing what-ifs, a reminder that the universe's greatest mysteries might be hiding in plain sight, written in light we're only learning to read. Stretching across billions of light-years, quasar light acts like a cosmic barcode etched with dark lines that tell the story of everything it's passed through. These absorption lines, known as the Lyman Alpha Forest, aren't just road marks in the universe. They're tangled up with the cosmic ultraviolet background in ways that both clarify and confuse our search for answers. Each line represents hydrogen gas clouds absorbing specific wavelengths of light, but collectively they form a labyrinthine record of the universe's structure and its secrets. So how does this forest connect to the CUVB? Imagine shining a flashlight through layers of stained glass. Each pane tints the light differently, and by studying those changes, you could reverse engineer the glass's composition. Quasar light does the same thing. As ultraviolet photons travel toward us, hydrogen atoms in intergalactic clouds snatch them at precise wavelengths, leaving gaps in the spectrum. The density, temperature, and motion of these clouds imprint patterns that astronomers use to map the universe's invisible scaffolding. But here's the twist: some of those absorbed photons don't just vanish. They're re-emitted, scattered in all directions, and a fraction likely weave into the diffuse glow we call the CUVB. This creates a chicken or egg dilemma. Are we seeing background light that's been filtered through the Lyman alpha forest, or is the forest itself contributing to the background? The answer could reshape how we interpret both. For instance, if certain absorption lines appear weaker than expected, it might mean the gas clouds are being illuminated by an external UV source, possibly the CUVB. Conversely, discrepancies in the background's intensity might trace back to how densely the Lyman alpha clouds are clustered in a given region. It's a hall of mirrors where every reflection changes the next. Complicating matters further, the forest isn't static. Over cosmic time, galaxies and quasars ionize nearby hydrogen, clearing fog from patches of the forest and altering how light propagates. This means the Lyman alpha patterns near a young quasar differ from those near an older one, yet the CUVB integrates light from all epochs. Untangling this requires near clairvoyant precision, separating which UV photons are fresh from modern galaxies, which are relics of reionization, and which have bounced through the forest's ever-shifting trees. Yet for all its chaos, the Lyman alpha forest offers clues the CUVB alone can't. By comparing absorption lines in quasars at varying distances, astronomers glimpse how ultraviolet transparency has evolved, a key to solving whether the background's unevenness stems from ancient events or ongoing processes. New instruments like the James Webb Space Telescope are sharpening this view, probing fainter quasars to expand the forest's map. Every line decoded narrows the gap between the universe we see and the one we're still learning to read. The irony: the very feature that obscures our view might hold the flashlight to illuminate it. The universe has a fever, and no one knows why. When astronomers measure the cosmic ultraviolet background, they expect to find a relatively even temperature, like the steady warmth of a room after the heater's been on for hours. Instead, they're staring at a cosmic thermometer gone haywire, with some patches of the CUVB blazing hotter than simulated supernova, while others register surprisingly chilly. These wild temperature swings aren't just curious, they defy our best models of how energy should distribute across space. Take the hottest anomalies first. Certain regions of the CUVB emit ultraviolet light with energy levels that suggest temperatures in the millions of degrees, far too high for typical starlight or even quasar radiation. One leading theory points to shock waves from colliding galaxy clusters, where gravitational energy transforms into heat, like cosmic tsunamis vaporizing everything in their path. But here's the catch: many of these ultra-hot zones float in seemingly quiet areas of space, nowhere near the violent mergers that should produce such extreme conditions. It's as if someone snuck blowtorches into the cosmic basement and forgot to turn them off. Then there are the cold spots, regions where the ultraviolet light appears oddly subdued, as if filtered through an invisible cosmic air conditioner. Some align with known voids, those vast bubbles of near-nothingness between galaxy filaments. Yet others overlap with areas rich in galaxies, which should theoretically pump out enough UV radiation to keep things warm. The coldest readings suggest temperatures barely above the cosmic microwave background's chill, raising questions about what could absorb or scatter so much energy without leaving a trace. Digging deeper reveals stranger patterns. The temperature variations don't always match the distribution of matter, visible or dark. In some cases, hot and cold patches appear to ripple outward from central points like thermal echoes, hinting at ancient, unseen cataclysms. Other fluctuations seem tied to the universe's large-scale structure, as if dark matter's hidden web somehow conducts heat in ways we can't yet model. The most baffling examples show rapid shifts over relatively small distances, with temperatures swinging dramatically across regions just a few million light-years wide. What's behind this thermal chaos? One provocative idea involves primordial magnetic fields, relics from the Big Bang that could channel energy unevenly through space like invisible gutters. Another suggests the answer lies in the CUVB multiple origins. Perhaps different sources dominate in different regions, creating a patchwork of temperatures. For instance, areas where decaying dark matter dominates might run hotter, while zones flooded by faint dwarf galaxies stay cooler. There's even speculation that we're seeing artifacts from the universe's first microseconds, when quantum fluctuations seeded temperature differences that never fully evened out. Untangling this paradox requires tools sensitive enough to map the CUVB thermal fine structure while filtering out local interference. Upcoming missions like ESA's Ariel telescope aim to do just that, analyzing ultraviolet light with spectrometers precise enough to detect temperature variations smaller than a star's surface. Meanwhile, supercomputer simulations are testing whether known physics can recreate these extremes, or if we're missing a fundamental piece of the cosmic energy puzzle. Every anomaly, every unexpected hotspot or cold streak, forces us to reconsider how energy flows through the universe and whether the cosmos plays by thermodynamic rules we've yet to fully grasp. One thing's certain, the temperature paradox isn't just about filling gaps in our knowledge. It's a window into the universe's hidden plumbing, revealing how energy sneaks, surges, and sometimes stalls on its journey through the void. Cracking this code could rewrite how we understand everything from galaxy formation to dark matter's role in shaping the cosmos. After all, if the universe can't even keep its temperatures straight, what other secrets is it keeping? If the cosmic ultraviolet background were a movie, we'd only be seeing the final frame, a single snapshot of light that's traveled billions of years to reach us. But what if we could rewind the cosmic tape? Understanding how this glow has transformed over time isn't just academic curiosity. It's a direct line to the universe's most dramatic chapters, from the explosive birth of the first galaxies to the quiet expansion of modern space. The clues start with redshift, the stretching of light waves as the universe expands. Distant objects appear redder because their light has traveled farther, carrying older signals. By measuring the CUVB properties at different redshifts, astronomers effectively slice cosmic history into layers like tree rings. Younger, closer galaxies show us recent ultraviolet output, while fainter, more redshifted light carries whispers from eras when the universe was half its current age or less. The startling discovery: the background's intensity hasn't faded evenly. Instead, it seems to pulse brighter during certain epochs, dimmer in others, as if the cosmos has been turning its UV dial up and down. One pivotal moment stands out, around redshift 2, which translates to roughly 3 billion years after the Big Bang. The CUVB appears to have hit a peak. This coincides with the universe's star-forming heyday, when galaxies were churning out stars at rates unmatched before or since. The ultraviolet glow from those countless young, hot stars should have lit up the cosmic background like a firestorm. Yet when researchers compare the expected surge to actual measurements, the numbers diverge. Either something was absorbing vast amounts of UV light during this golden age, or our models of galaxy evolution are missing crucial players. Then there's the Dark Ages paradox. Early in cosmic history, before galaxies fully formed, the CUVB should have been nearly black, yet some observations hint at faint ultraviolet signals persisting even then. Could these be traces of the universe's first stars, so massive and short-lived they left an indelible mark? Or do they point to exotic energy sources, like evaporating primordial black holes or decaying dark matter, flickering in the void long before modern stars took the stage? The plot thickens when we examine the background's spectral fingerprints. The mix of ultraviolet wavelengths changes subtly across cosmic time, reflecting shifts in dominant light sources. Younger epochs show signatures of active galactic nuclei, quasars, and their kin, while older layers bear the imprint of starlight. But sandwiched between are anomalies, wavelengths that don't match any known emitter, suggesting lost chapters in the universe's energy narrative. Unraveling this timeline isn't just about filling gaps, it's about testing our grandest theories. Did reionization happen in bursts or a steady rise? How did early supermassive black holes influence their surroundings? Even the expansion rate of the universe leaves traces in the CUVB evolution, offering an independent check on our measurements of cosmic acceleration. Every inconsistency between prediction and observation could mean rewriting textbooks. Right now, we're like historians trying to reconstruct a civilization from scattered artifacts. But next-generation telescopes promise sharper vision across cosmic time. NASA's forthcoming Habitable Worlds Observatory aims to dissect the CUVB history with unprecedented precision, potentially revealing how ultraviolet light shaped the conditions for life itself. The story isn't just written in the stars, it's painted in ultraviolet across the sky, waiting for us to read between the lines. Studying the cosmic ultraviolet background is like trying to listen to a whisper in the middle of a hurricane. Earth itself keeps getting in the way. Our atmosphere acts like a thick, ultraviolet absorbing blanket, soaking up nearly all incoming UV radiation before it reaches the ground. This means ground-based telescopes, no matter how powerful, are practically blind to the CUVB's subtle glow. To even begin detecting it, we have to launch instruments above this atmospheric barrier into the unforgiving environment of space. Even then, the challenges multiply. Space telescopes like Hubble have revolutionized our view, but they weren't designed specifically for the CUVB unique demands. Imagine trying to photograph a dimly lit room using a camera optimized for sunlight. You'd miss the faintest details. The background signal is incredibly weak, often drowned out by stray light from brighter sources like nearby stars or even reflected sunlight bouncing off interstellar dust. Filters and shielding help, but they're not perfect. A single stray photon from a distant quasar can skew measurements, forcing astronomers to spend months, sometimes years, carefully subtracting noise from their data. Then there's the sensitivity problem. Unlike visible light, ultraviolet photons pack enough energy to damage the very detectors meant to catch them. Over time, prolonged exposure degrades instrument performance, like a microphone slowly burning out from too many loud concerts. Hubble's cosmic origin spectrograph, for instance, has to balance observation time with regular calibration checks to compensate for this wear and tear. Newer telescopes, like ESA's upcoming UVEX mission, are being built with more resilient materials, but even they'll face the same fundamental trade-off. The harder you push to detect faint signals, the faster your tools degrade. Resolution adds another layer of difficulty. The CUVB isn't just faint, it's diffuse, spread evenly across the entire sky. Traditional telescopes excel at zooming in on specific targets like galaxies or nebulas, but mapping something as vast and uniform as the ultraviolet background requires wide-field instruments with eagle-eyed precision. It's the difference between using a magnifying glass to study a single leaf and trying to photograph every tree in a forest simultaneously. Current technology forces compromises. You can either cover large swaths of the sky with lower detail or focus narrowly and miss the bigger picture. Perhaps the most frustrating hurdle is time. Unlike explosive cosmic events that flare and fade, the CUVB is a perpetual, whisper-quiet phenomenon. To gather enough data for meaningful analysis, telescopes must stare at the same patch of sky for hundreds of hours, like straining to hear a distant conversation through a staticky radio. And because space-based observation time is fiercely competitive, shared among thousands of researchers studying everything from exoplanets to supernova, securing those precious hours is a battle in itself. Yet these obstacles aren't just barriers, they're invitations to innovate. Next-generation telescopes are incorporating adaptive optics to filter out interference, while machine learning helps sift signal from noise in unprecedented ways. Balloon-borne instruments floating high in the stratosphere offer cheaper alternatives to full space missions. Every technical limitation sparks new solutions, turning the study of the CUVB into a proving ground for the next era of cosmic exploration. After all, the universe's greatest mysteries rarely surrender their secrets easily, but that's what makes the hunt so thrilling. We've mapped galaxies by the million spirals, ellipticals, starbursts, but what if the cosmos is teeming with an entire hidden population, too faint to see yet bright enough to flood the universe with ultraviolet light? This is the tantalizing premise behind the ultra-faint galaxy hypothesis, a potential solution to the cosmic ultraviolet background's biggest mystery. These aren't just dim versions of familiar galaxies, they're cosmic phantoms so diffuse they'd make a wisp of smoke look solid. Their stars are scattered so thinly that if you stood in one, the night sky would appear nearly black, punctuated only by a handful of distant suns. Yet collectively, their numbers could be staggering, forming an invisible tapestry woven through the voids between brighter galaxies. How could something so faint make such a noticeable mark? Imagine you're in a pitch-black forest holding a single match. It barely lights your face, but if thousands of others lit their matches at the same time, the whole woods would glow. Ultra-faint galaxies work the same way. Individually, their ultraviolet output is negligible, but across billions of years and trillions of potential galaxies, their combined light might saturate the cosmos. Simulations suggest these dwarfs could outnumber traditional galaxies 100 to 1, remnants of the universe's earliest star-forming attempts, stunted by their lack of dark matter or shredded by tidal forces. The catch, finding them pushes telescopes beyond their limits. Current instruments like Hubble can spot ultra-faint dwarfs only in our cosmic backyard, say within a few 100 million light-years. Beyond that, their light stretches into near nothingness, drowned out by the glare of neighboring stars and galaxies. Even worse, many might lack the heavy elements that give galaxies their telltale spectral signatures, rendering them nearly invisible to traditional detection methods. It's like searching for a single candle hidden behind a spotlight. That's where next-gen telescopes come in. NASA's upcoming Nancy Grace Roman Space Telescope, with its infrared eyes and panoramic field of view, could be the game-changer. By peering into wavelengths less affected by cosmic expansion, Roman might catch these ghosts by their heat rather than their light. Meanwhile, ground-based behemoths like the extremely large telescope will deploy adaptive optics to cancel atmospheric blur, sharpening our view of the faintest structures. The real hope lies in their synergy, combining Roman's wide surveys with pinpoint follow-ups from other observatories to confirm these galaxies exist beyond our local universe. But the most exciting possibility isn't just finding them, it's learning what they'd reveal. If ultra-faint galaxies dominate the CUVB, their distribution should mirror the background's uneven glow, explaining why some cosmic regions appear inexplicably bright. Their star formation rates could rewrite our understanding of how small galaxies contribute to reionization, and their chemistry might preserve pristine samples of the universe's first elements, untouched by later supernova. Some theorists even speculate they could be factories for unconventional dark matter, their feeble gravity hiding exotic particle interactions. The hunt is more than a technical challenge, it's a philosophical shift. For centuries, astronomy focused on the cosmos' brightest beacons, assuming they held the answers. Now, we're realizing the universe's secrets might be whispered by its quietest inhabitants, their faint ultraviolet hum a clue we're only beginning to decipher. Every time a telescope peers deeper, we're not just looking farther, we're learning to see in the dark. Active galactic nuclei, the blazing hearts of galaxies where supermassive black holes feast on cosmic gas, should be prime suspects in the case of the cosmic ultraviolet background. These monstrous engines, capable of outshining entire galaxies, blast out ultraviolet radiation as they devour matter, making them seem like obvious culprits. Yet the evidence is anything but clear-cut. While some regions of the CUVB align neatly with clusters of AGN, others glow fiercely where no active nuclei are found, sparking a heated debate among astronomers. Are we overestimating their role or missing a critical piece of the puzzle? The argument for AGN dominance starts with sheer power. A single active nucleus can produce more ultraviolet light in an hour than the sun will emit in its entire lifetime. Multiply that by millions of AGN scattered across the cosmos, and you've got a theoretical UV powerhouse. Observations seem to back this up. Studies of nearby galaxies show their active cores contribute significantly to local ultraviolet fluxes. Extrapolating that across the universe, it's easy to assume AGN could collectively account for much of the CUVB glow, but scratch the surface and contradictions emerge. For one, AGN are fickle. Their brightness fluctuates wildly over cosmic timescales, flickering like candles in a drafty room. The CUVB, by contrast, is remarkably steady, a persistent hum that doesn't match the erratic behavior of black hole outbursts. Then there's the distribution problem. Active nuclei tend to cluster in dense regions of space where galaxies collide and gas is plentiful. Yet the ultraviolet background appears almost uniform, even in desolate cosmic voids where AGN are virtually non-existent. The plot thickens when you consider obscuration. Many AGN are shrouded in thick cocoons of dust, which absorb their ultraviolet light and re-emit it at longer infrared wavelengths. This means a significant fraction of their energy might never reach the cosmic background at all, slipping through our observational net. Some theorists argue we're only seeing the tip of the iceberg, that hidden populations of obscured AGN could be pumping out UV light we can't directly detect. But if that's true, why don't their infrared signatures leave clearer imprints on other parts of the electromagnetic spectrum? On the flip side, AGN skeptics point to timing. The universe's peak of AGN activity occurred around 10 billion years ago, yet the CUVB properties suggest a more recent and sustained contribution. There's also the ionization mystery. Active nuclei emit hard ultraviolet photons perfect for stripping electrons from atoms, but measurements of intergalactic gas show ionization levels that don't quite match predictions based solely on AGN output. It's like finding a murder weapon that doesn't fit the wound. Perhaps the truth lies somewhere in between. New research suggests AGN might dominate the CUVB in specific environments, like crowded galaxy clusters, while other sources, like faint dwarf galaxies or decaying dark matter, take the lead elsewhere. Or maybe we've underestimated how efficiently AGN light propagates through space, with intergalactic dust acting as a cosmic diffuser, scattering their ultraviolet glow far beyond their immediate surroundings. Upcoming telescopes like the James Webb Space Telescope and the European Extremely Large Telescope aim to settle the debate by hunting for faint AGN signatures in the background spectral fingerprints. What makes this controversy so fascinating isn't just the scientific stakes, it's how it forces us to rethink black holes' role in shaping the universe. If AGN are indeed major players, they're not just destructive monsters. They're cosmic lighthouses, their ultraviolet beams heating intergalactic gas and regulating star formation across billions of light years. But if their impact has been overstated, it means something far stranger is painting the cosmos with UV light, something we've yet to fully imagine. Either way, the answer won't just solve a mystery, it'll redefine how we see the universe's hidden engines. Stretching across the cosmos like an immense spiderweb made of galaxies and gas, the cosmic web forms the hidden skeleton of the universe. Most of it remains invisible, dark matter filaments weaving through the voids, pulling galaxies into vast interconnected threads. But here's the tantalizing possibility. What if the cosmic ultraviolet background isn't just random starlight, but a glowing trace of this elusive architecture? The idea isn't as far-fetched as it sounds. If even a fraction of the web's ordinary matter, those gossamer strands of hydrogen gas, were energized by cosmic radiation or shock waves, they might emit just enough ultraviolet light to paint the outlines of the universe's largest structures. Think of it like a celestial blacklight experiment. Under normal circumstances, the cosmic web's filaments are too faint and diffuse to spot directly. But if something were to excite their hydrogen atoms, perhaps ultraviolet photons from ancient quasars or heat from colliding galaxy clusters, those filaments could fluoresce ever so slightly, imprinting their patterns onto the CUVB. We wouldn't see them as crisp lines, of course. Instead, the background's subtle fluctuations, those patches of extra brightness or unexpected dimness, might align with where supercomputer simulations predict the web's densest strands should lie. It's the universe's version of connecting the dots with ultraviolet light as our guide. Evidence for this is still circumstantial but compelling. Some regions of the CUVB show faint enhancements that mirror the predicted locations of cosmic web filaments, like shadows cast by unseen scaffolding. Others reveal puzzling correlations between ultraviolet intensity and known galaxy clusters, hinting that the web's structure might be channeling or amplifying the light in ways we don't yet grasp. Then there's the temperature factor. Filaments warmed by passing shock waves or cosmic rays might leak UV radiation at specific energies, creating spectral signatures that stand out against the background's smoother glow. Yet skeptics point to the noise in the data. The cosmic web's signal, if it exists in the CUVB, is buried under a cacophony of other sources: starlight from galaxies, radiation from quasars, even the afterglow of long-dead stars. Isolating the web's contribution requires statistical wizardry, teasing out patterns so subtle they could easily be illusions. Even then, there's the question of physics. Do filaments really retain or emit enough energy to leave a detectable mark? Some simulations say yes, showing that collisions within the web could heat gas to millions of degrees, sparking ultraviolet emission. Others suggest the signal would be too feeble, lost in the cosmic static. The hunt for answers is driving astronomers to refine their tools. Upcoming missions like the European Space Agency's Athena X-ray Observatory won't see ultraviolet light directly, but by mapping the web's hottest gas, they could pinpoint where UV emission ought to be strongest. Meanwhile, next-generation spectrographs are dissecting the CUVB light with sharper precision, searching for telltale wavelengths that might betray the web's presence. A confirmed detection wouldn't just solve a mystery, it would open a new window into the universe's structure, letting us trace dark matter's distribution by the UV glow of the ordinary matter it drags along. Imagine the implications. Instead of inferring the cosmic web from galaxy positions or gravitational lensing, we might one day see it directly, its faint ultraviolet threads woven through the darkness. That glow could reveal how efficiently the web funnels gas into galaxies, how shock waves ripple through its strands, even how dark matter's invisible grip shapes the flow of light itself. The cosmic web has always been the universe's hidden blueprint, but with the CUVB help, we might finally be learning to read it. Hydrogen isn't the only element that had to wake up after the cosmic dark ages. Helium, its heavier sibling, went through its own dramatic reionization, and the echoes of that upheaval might still linger in the cosmic ultraviolet background. While hydrogen's reionization gets most of the attention, helium's story is just as pivotal, unfolding later and requiring even more energy to strip its electrons away. The universe had to grow up a bit before it could tackle this challenge, meaning helium reionization acts like a timestamp, a marker of when the cosmos transitioned from its chaotic youth into something more mature. The process works like this: neutral helium atoms left over from the Big Bang float through space until they're hit by ultraviolet photons so energetic they can knock loose not just one but both of helium's electrons. This requires light with wavelength shorter than 228 angstroms, far more extreme than what's needed for hydrogen. Only the most powerful sources in the universe can muster that kind of energy, like quasars powered by supermassive black holes feasting on vast amounts of matter. When these cosmic blowtorches flickered on billions of years ago, they didn't just light up their surroundings, they fundamentally altered the state of helium across the cosmos, carving transparent bubbles in what was once an opaque fog. The question is, did that transformation leave traces we can still detect? Some researchers believe the CUVB holds subtle spectral imprints, specific wavelengths where the background light dips or surges in ways that match predictions of helium reionization. Imagine a detective dusting for fingerprints and finding a partial match. The patterns aren't perfect, but they're tantalizingly close. Other clues come from the timing. If we can pinpoint when the bulk of helium reionization occurred, likely around redshift 3 to 4, when quasars were at their peak, it could explain why certain regions of the ultraviolet background seem oddly structured, as if something monumental happened there long ago. Yet mysteries remain. If helium reionization was so transformative, why doesn't the CUVB show more obvious scars? One possibility is that quasars weren't the sole players. Theoretical models suggest that less glamorous sources, like ultra-hot gas in galaxy clusters or even decaying dark matter, could have contributed extra UV photons, smoothing out the process and diluting its signal. Alternatively, the fingerprints might be there, just buried under noise from later events, like trying to hear a faint song while standing next to a roaring waterfall. Untangling this requires instruments capable of dissecting the CUVB spectrum with surgical precision, isolating the exact wavelengths where helium's ghost should whisper. What makes this detective work so valuable isn't just about helium. It's a window into the universe's adolescence. By studying when and how this reionization unfolded, we learn how energy moved through the cosmos during a critical phase of its growth. Did quasars light up the universe in a sudden flash, or was it a slow, uneven awakening? The answers could reshape our understanding of everything from galaxy formation to the life cycles of supermassive black holes. The CUVB might hide more than just light. It could hold the diary of a cosmos coming into its own. The farther you look into space, the farther back you peer in time, but when it comes to the cosmic ultraviolet background, this simple rule becomes a tangled puzzle. Is the glow we see mostly coming from nearby galaxies and quasars lighting up our cosmic neighborhood? Or is it the accumulated whisper of countless distant sources, their light stretched and faded over billions of years? This isn't just academic trivia. The answer could rewrite how we understand the universe's energy budget and evolution. Take the case for local dominance first. Nearby galaxies, while less numerous than their distant counterparts, pack a serious ultraviolet punch. Think of the Andromeda Galaxy, just 2.5 million light-years away, pumping out UV radiation from its bustling star-forming regions. Across our local cosmic bubble, dozens of similar galaxies contribute their light, creating a foreground haze that might skew our measurements. Even intergalactic stars, rogue suns flung out of their home galaxies, could add to the mix, their combined glow subtly inflating the CUVB apparent brightness. If local sources are the main players, it implies the universe's modern era is far more active than we've assumed, with nearby objects shouldering more of the ultraviolet load than models predict. But the evidence isn't so clear-cut. When astronomers subtract known local contributions from the CUVB signal, a substantial portion remains too much to explain without invoking distant sources. That's where the redshifting challenge comes in. Ultraviolet light from faraway galaxies gets stretched into longer, redder wavelengths as the universe expands, meaning some of it slips out of the traditional UV range entirely. Yet careful spectral analysis reveals residual light that aligns with expectations for redshifted sources. The kicker: distant galaxies in the early universe were often hotter and more star-rich than their modern counterparts, making them disproportionately bright in UV despite their extreme distances. Complicating matters further is the Olbers paradox effect. Just as the night sky isn't blindingly bright because distant stars' light dims with distance, the CUVB smoothness suggests a balance between nearby and faraway sources. If distant objects dominated, we'd expect more pronounced fluctuations, bright patches where ancient galaxy clusters once thrived, dark voids where cosmic expansion diluted their signals. Instead, the background's relative uniformity hints at a delicate equilibrium, with local and distant sources blending into a cosmic average. The debate spills over into practical astronomy. If local sources skew the CUVB, telescopes might need recalibration to avoid overcounting nearby objects when mapping the universe's early UV output. Conversely, if distant galaxies contribute more than expected, our models of cosmic star formation rates could be drastically underestimated. Some theorists even propose a hybrid solution that the background structure changes with wavelength, with shorter UV bands dominated by local emitters and longer bands carrying the echoes of primordial starlight. Cutting-edge observations aim to settle the score. Projects like the Hubble Ultra Deep Field have peered into the distant universe, tallying faint galaxies to estimate their collective ultraviolet output. Meanwhile, missions like the upcoming James Webb Space Telescope's NIRCam instrument will hunt for redshifted UV light that slipped into the infrared, offering a clearer picture of what's truly local versus what's been traveling across eons. Each dataset tightens the noose around this mystery, forcing us to confront whether we're living in an unusually UV-bright pocket of the cosmos, or if the universe's past is shining far brighter than we ever imagined. What's at stake isn't just a technicality. If distant sources dominate, it implies the early universe was even more ferociously energetic than simulations suggest, with galaxies churning out stars at rates that defy modern parallels. But if local sources carry the day, it means our corner of space is oddly privileged, bathed in ultraviolet from neighbors we've underestimated. Either outcome forces a reckoning, not just with the CUVB origins, but with how we measure the universe's pulse across time and space. The light isn't just arriving, it's telling a story. We're still learning how to listen. Light doesn't just travel, it dances. Normally, the photons streaming from stars and galaxies vibrate in every direction, their electric fields oscillating chaotically like a crowd of people waving their arms at random. But sometimes, something nudges those vibrations into alignment, creating what scientists call polarized light. This is where the cosmic ultraviolet background throws us another curveball, because scattered across its faint glow, patches of ultraviolet light appear strangely polarized, as if something out there is choreographing their movements. The discovery sparked immediate debate. Polarization usually happens when light interacts with magnetic fields or scatters off particles, like sunlight reflecting off the ocean and forming a glare. But the CUVB polarization doesn't neatly match either explanation. If magnetic fields were responsible, they'd need to be unimaginably vast, stretching across intergalactic space with a coherence and strength that defies our current models. We know galaxies and galaxy clusters host magnetic fields, but these taper off quickly in the voids between them. Yet the polarized patches in the ultraviolet background appear even in regions where no known galaxies or quasars exist, as if invisible hands are combing the light into order across billions of light years. Then there's the scattering theory. When ultraviolet photons bounce off free electrons or dust grains, they can become polarized, much like how polarized sunglasses filter reflected glare. But the intergalactic medium is so sparse, just a few atoms per cubic meter, that it shouldn't scatter enough light to create detectable polarization, unless, of course, we're missing something. Some researchers propose that undiscovered clouds of ultra-fine dust or exotic particles might lurk between galaxies, acting like cosmic polarizers. Others wonder if the light is being reshaped by something even stranger. Perhaps the faint echoes of primordial gravitational waves rippling through space-time and subtly twisting the light's orientation as it travels. The plot thickens when we examine the patterns. The polarization isn't uniform. It clusters in specific regions, often aligning with the cosmic web's predicted filaments. Could these be traces of shock waves rippling through the gas along those vast structures, imparting order to passing photons? Or do they mark the aftermath of ancient quasar outbursts, where jets of charged particles once surged through space, leaving behind magnetized wakes that still influence light billions of years later? Solving this mystery isn't just academic. Polarized light carries hidden information about the environments it's passed through, like a cosmic FedEx sticker detailing its journey. If we can decode it, we might uncover the strength and structure of magnetic fields in the emptiest parts of the universe, or even glimpse exotic physics beyond the standard model. Instruments like the upcoming Light-Bird satellite aim to map cosmic polarization with unprecedented precision, while advanced simulations test whether known physics can reproduce these signals, or if we're staring at the footprints of something entirely new. For now, the polarization of the cosmic ultraviolet background remains one of its most tantalizing riddles. It's a reminder that light isn't just about brightness or color. Sometimes the universe speaks in subtler ways, and we're only beginning to learn its language. Every polarized photon could be a clue pointing toward forces and structures we've yet to imagine, hidden in plain sight. Simulations have a funny way of humbling us. No matter how sophisticated our models become, the universe always finds a way to defy expectations. Take the so-called photon underproduction crisis, where even our most advanced calculations consistently predict far less ultraviolet light than we actually observe. It's as if the cosmos has a hidden flashlight shining in the dark, and we're scrambling to figure out where the batteries came from. This discrepancy isn't just a minor accounting error. It's a gaping hole in our understanding of cosmic energy flows. Modern simulations, which meticulously track the formation of galaxies, the birth and death of stars, and the output of quasars, suggest the universe should produce roughly half the ultraviolet light we detect in the cosmic ultraviolet background. That's like pouring a gallon of water into a jug and watching it somehow fill 2 gallons instead. Where is all this extra light coming from? One glaring possibility is that our simulations are missing entire categories of ultraviolet emitters. Think about it. If you were modeling a city's energy usage but forgot to account for streetlights, your numbers would be wildly off. Similarly, astrophysicists might be overlooking populations of ultra-faint galaxies, rogue stars ejected into intergalactic space, or even exotic objects like intermediate mass black holes, all of which could be stealthily pumping UV photons into the cosmic void. Some theorists argue we've underestimated the efficiency of star formation in the early universe, meaning young galaxies were churning out far more ultraviolet radiation than we've given them credit for. But there's a darker twist. What if the mismatch isn't about missing sources but flawed physics? Our models rely on well-tested laws of how stars and gas behave, but what if ultraviolet light interacts with the intergalactic medium in ways we haven't accounted for? Perhaps photons are being scattered or amplified as they travel, creating optical illusions that inflate their apparent numbers. Or maybe the universe's expansion isn't as uniform as we think, stretching some wavelengths more than others and skewing our measurements. The most provocative explanation: our theories about dark matter might need a rewrite. If certain dark matter particles decay or collide, they could be injecting extra ultraviolet photons into the cosmos like invisible factories humming away in the darkness. While this idea remains speculative, it's a stark reminder that the photon underproduction crisis isn't just about light. It's a symptom of something deeper, a clue that our cosmic ledger might be missing entire columns of entries. Until we solve this, every measurement of the cosmic ultraviolet background comes with an asterisk. Are we seeing the universe as it truly is, or through a lens we don't yet understand? The answer could redefine not just our models but our place in the cosmic story. Before galaxies lit up the cosmos, before even the first black holes began their feast, the universe was home to its very first generation of stars, population 3. These stellar titans were unlike anything we see today, born from pristine clouds of hydrogen and helium left untouched since the Big Bang. Towering hundreds of times more massive than our Sun, they blazed with ultraviolet ferocity, then died young in cataclysmic explosions that seeded the cosmos with heavier elements. But while these stars themselves vanished billions of years ago, their ghosts might still haunt the cosmic ultraviolet background, whispering to us across the eons. The idea hinges on a simple but profound question: where did all that ultraviolet energy go? Population 3 stars didn't just shine, they flooded the early universe with photons powerful enough to rip electrons from atoms, driving the epoch of reionization. Conventional wisdom says their light stretched and faded as the cosmos expanded, redshifting into oblivion. Yet some theorists argue traces could linger, woven into the CUVB faint tapestry. Imagine a firework that burned out centuries ago. You wouldn't see its flash, but if enough smoke particles lingered, they might still scatter sunlight in detectable ways. Similarly, the first star's radiation could have imprinted on the intergalactic medium, leaving subtle spectral fingerprints for us to find. Hunting these echoes is like sifting through a cosmic crime scene. Population 3 stars likely emitted light at specific ultraviolet wavelengths, shaped by their unique chemistry, pure hydrogen and helium, uncontaminated by heavier elements. If the CUVB contains unexpected spikes at these wavelengths, especially in regions devoid of modern stars, it could be the smoking gun of their ancient presence. Some observations already hint at anomalies, patches of ultraviolet light too energetic to explain with known sources, like finding footprints in ash where no one should have walked. Then there's the supernova factor. When these behemoths exploded, they didn't just vanish, they hurled their enriched guts across space, heating surrounding gas to millions of degrees. That heat could have persisted, re-radiated over billions of years as softer ultraviolet light. Simulations show these shockwaves might have carved vast bubbles in the intergalactic medium, structures so large they'd still influence how UV travels today. It's as if the first stars didn't just die, they left behind invisible ruins, their outlines etched into the very fabric of space, yet skeptics point to the odds. The universe has stretched and churned so much since those early epochs that any direct signal should be hopelessly diluted, like trying to taste a single grain of salt dissolved in an ocean. Others argue we're conflating cause and effect. Anomalies in the CUVB could stem from modern phenomena we don't yet understand, not primordial relics. But the most tantalizing counterargument: we might be looking in the wrong place. Instead of chasing light, some scientists propose hunting for the chemical debris of population 3 stars, specific ratios of elements like carbon or oxygen that only their supernova could produce. Finding these in tandem with ultraviolet anomalies could forge an ironclad link. The search is pushing telescopes to their limits. Instruments like the James Webb Space Telescope are scouring distant galaxies for signs of population 3's descendants, stars slightly younger but still bearing their distinctive elemental signature. Meanwhile, next-generation spectrographs dissect the CUVB light with ever finer precision, separating potential primordial whispers from the noise of modern astrophysics. Every mismatch between prediction and observation is a clue, every unexplained wavelength a potential message from the universe's fiery dawn. What makes this mystery so compelling isn't just the science, it's the sheer poetry of the idea. The cosmic ultraviolet background might be more than a puzzle to solve. It could be a living archive carrying the final breaths of stars so ancient they predate every galaxy, every planet, every ingredient needed for life. If their light still flickers, however faintly, it means we're not just observers of the cosmos, we're heirs to a legacy written in ultraviolet, one we're only beginning to decipher. The cosmic ultraviolet background isn't alone. It's part of an entire choir of cosmic hums, each singing at different wavelengths. From the microwave afterglow of the Big Bang to the faint infrared glow of distant dust clouds, the universe is awash in diffuse light. But the CUVB stands apart not just for what it reveals, but for how it dances with these other backgrounds, creating a symphony of radiation that traces the universe's hidden rhythms. Unlike the steady glow of the cosmic microwave background or the warm infrared haze of interstellar dust, ultraviolet light is restless, energetic, and deeply tied to the birth and death of stars. Start with the infrared background, the CUVB closest counterpart. While ultraviolet light comes from young, hot stars and violent quasars, the infrared background arises from cooler, dust-shrouded objects. Think of the difference between a blowtorch and a space heater. Galaxies wrapped in thick veils of cosmic dust absorb UV light and re-emit it as infrared, effectively transforming the universe's most energetic photons into a warmer, longer wavelength glow. This interplay creates a cosmic seesaw. Where the CUVB dips, the infrared background often surges, revealing regions where dust is actively smothering starlight. In some cases, this relationship helps solve puzzles like why certain patches of the ultraviolet sky seem oddly dark, only to blaze brightly in infrared surveys. Then there's the X-ray background, a crackling haze of ultra-high-energy photons. At first glance, X-rays and UV seem worlds apart. One emitted by superheated gas swirling around black holes, the other by star-forming galaxies. But they're intimately connected. When quasars flood space with ultraviolet radiation, some of that light can get boosted to X-ray energies through collisions with fast-moving electrons in intergalactic space. This means portions of the X-ray background might actually be ultraviolet light in disguise, like a whisper amplified into a shout. Conversely, X-rays from galaxy clusters can ionize surrounding gas, making it more transparent to UV photons and subtly sculpting the CUVB structure. What makes the ultraviolet background truly unique, though, is its sensitivity to the universe's most transformative events. The cosmic microwave background freezes a single moment, the universe's infancy, while the infrared and X-ray backgrounds reflect slower, ongoing processes. But the CUVB captures both the fireworks and the fallout, the explosive deaths of massive stars, the awakening of the first galaxies, even the slow decay of hypothetical dark matter particles. It's a living record, updated in real time as light streams across billions of years. This interconnectedness isn't just academic, it's practical. By comparing these backgrounds, astronomers can triangulate hidden phenomena. For instance, discrepancies between the predicted and observed UV to infrared ratios have exposed missing populations of dust-obscured galaxies. Unexplained correlations between X-ray and UV fluctuations have hinted at large-scale magnetic fields weaving through intergalactic space. Even the cosmic microwave background, when studied alongside the CUVB, reveals how reionization ultraviolet flood might have left faint scars on the universe's oldest light. Yet for all these links, the ultraviolet background remains stubbornly enigmatic. While other wavelengths fit relatively neatly into our models, the CUVB refuses to be fully explained, its excesses and asymmetries pointing to gaps in our understanding. Maybe it's because ultraviolet light is so easily scattered, absorbed, and transformed a cosmic chameleon that never sits still long enough to be pinned down. Or perhaps it's because more than any other background, the CUVB is a palimpsest, layer upon layer of light from every epoch, waiting for us to peel them apart. One thing's certain, until we unravel how it fits into this broader electromagnetic tapestry, the universe's full story will stay just out of reach. The next decade could rewrite everything we know about the cosmic ultraviolet background, not with incremental steps, but with quantum leaps in technology. At the forefront is NASA LUVOIR, the Large UV Optical Infrared Surveyor, a behemoth telescope concept designed to see farther and fainter than anything before it. Imagine Hubble's precision combined with a light-collecting mirror up to 15 meters wide that's wide enough to spot a firefly hovering near a lighthouse from 10,000 miles away. LUVOIR ultraviolet spectrographs won't just map the CUVB, They'll dissect it, isolating individual wavelengths with such clarity that we could finally distinguish between light from decaying dark matter, primordial stars, and hidden galaxies. If the ultraviolet background is a tangled ball of yarn, LUVOIR is the needle that could unravel it thread by thread. Then there's HAB-X, the Habitable Worlds Observatory, with a different but equally revolutionary approach. While its primary mission is hunting Earth like exoplanets, its ultraviolet capabilities could turn it into the ultimate CUVB detective. Picture this: by blocking out the glare of nearby stars with a starshade the size of a baseball diamond, HAB-X would peer into the deepest, darkest voids precisely where the background's faintest signals hide. Its coronagraph might even spot ultra-faint dwarf galaxies currently lost in the noise, testing whether they're truly the missing ultraviolet sources we've been searching for. But the real game changer: these telescopes won't work alone. Combined with ESA's Ariel and the James Webb Space Telescope's infrared eyes, they'll create the first multi-wavelength map of the cosmic energy web. For instance, if LUVOIR spots an anomalous UV glow in a seemingly empty patch of sky, Webb could pivot to check for infrared heat from dust-shrouded galaxies, while Ariel analyzes the region's chemical fingerprints. It's like assembling a cosmic jigsaw puzzle where each telescope contributes pieces the others can't see. The breakthroughs on the horizon aren't just technical, they're philosophical. Suppose LUVOIR confirms that decaying dark matter contributes to the CUVB. That wouldn't just solve the photon underproduction crisis. It would hand us dark matter's identity on a silver platter, revealing its mass and decay rate through the ultraviolet light it emits. Or imagine HAB-X finding that the background's polarization aligns perfectly with simulations of the cosmic web's magnetic fields. Suddenly, we'd have proof that the universe's largest structures are threaded with invisible forces, shaping how light travels across billions of light years. And let's not forget the wildcards missions still in early design phases, like NASA Ultraviolet Explorer, or private ventures like the orbiting astronomical satellite for investigating stellar systems. Some propose fleets of tiny CubeSats, each carrying specialized UV filters, swarming like fireflies to cover the entire sky in unprecedented detail. Others envision balloon-borne telescopes floating above the stratosphere, where atmospheric interference drops to near zero, offering cheaper but equally transformative views. The most exciting possibility: these tools might uncover phenomena we haven't even dreamed of yet. Every time humanity builds a telescope with new capabilities, it doesn't just answer old questions, it reveals entirely new mysteries. The cosmic ultraviolet background has spent decades defying explanation, but the next generation of instruments won't just listen to its whispers. They'll help us hear the universe speaking in a language we're only beginning to understand. What if the cosmic ultraviolet background isn't just a puzzle, it's a window into realities beyond our own? Among the most speculative but electrifying theories is the idea that alternate universes or exotic physics might imprint faint signatures on the CUVB, leaving trails we could theoretically decode. Before you dismiss this as science fiction, consider this. The same quantum principles that govern subatomic particles also allow for the possibility of parallel worlds bubbling just beyond our perception. If even a fraction of their energy leaked into our universe, it might manifest as anomalies in the ultraviolet glow bathing the cosmos. Start with the multiverse hypothesis. In some versions of string theory, our universe exists on a vast brane, a membrane floating in higher dimensional space, with other branes hovering nearby like pages in a book. If two branes ever collided or brushed against each other, the energy released could have flooded our cosmos with radiation, including ultraviolet photons that lingered long after the event. The CUVB unexplained fluctuations, particularly those that don't align with known astrophysical sources, might be the cosmic equivalent of fingerprints on a window, evidence of something brushing past from outside. Then there's the shadow photon scenario. certain extensions of particle physics suggest our universe could be intertwined with a parallel one where light behaves slightly differently. Photons from that shadow realm might occasionally bleed into ours, their energy subtly distorting the ultraviolet background spectrum. It's like tuning a radio and catching static from a station broadcasting in a foreign language. The signal's there, but we don't yet know how to translate it. Critics, of course, raise valid objections. If alternate universes were seeping energy into ours, why wouldn't we see other, more obvious effects? Where are the gravitational ripples or temperature spikes in the cosmic microwave background? Proponents counter that ultraviolet light could be the ideal tracer, energetic enough to reveal faint interactions but common enough to hide in plain sight. After all, we only recently confirmed gravitational waves. Why not multiversal ones next? Even wilder ideas lurk at physics fringes. Some theorists propose that vacuum decay, a catastrophic phase transition where the universe's fundamental state collapses, could have left ultraviolet echoes in the CUVB. Others suggest primordial black holes formed in the early chaos might emit UV radiation as they evaporate via Hawking radiation, their demise marked by spectral fingerprints no ordinary star could replicate. The line between science and speculation here is razor thin, but that's what makes it thrilling. While most researchers focus on conventional explanations for the CUVB, a handful are developing tools to test these exotic possibilities. Future telescopes with ultra-precise spectrometers could scan for impossible wavelengths or polarization patterns that defy known physics. Until then, the multiverse remains a tantalizing what if a reminder that the universe's greatest mysteries often start where our imagination meets the unknown. Whether these ideas hold up or not, they serve a vital purpose, stretching our assumptions about what the cosmic ultraviolet background might reveal. After all, every radical theory was once dismissed as fantasy until evidence proved otherwise. The CUVB enigmas don't just challenge us to fill gaps in our knowledge, they dare us to wonder whether the gaps themselves lead somewhere extraordinary. Could the same ultraviolet glow that puzzles astronomers also shape the very conditions for life? The cosmic ultraviolet background might seem like a distant curiosity, but its faint reach could extend all the way to the surfaces of alien worlds, influencing which planets become cradles for biology and which remain barren wastelands. This isn't just about starlight from nearby suns, it's about the collective UV bath from the entire universe, a whisper of radiation that has persisted for billions of years, quietly tweaking the chemistry of planetary atmospheres. Take Earth's own history as a clue. Our planet's ozone layer, that fragile shield against harmful UV, didn't form overnight. It was built gradually as early life like cyanobacteria pumped oxygen into the atmosphere, where sunlight then split oxygen molecules, allowing ozone to coalesce. But what if the ambient ultraviolet background had been stronger during those critical eons? Excessive UV can break apart complex organic molecules, the building blocks of life, before they have a chance to assemble into something more. On the flip side, too little UV might stall chemical reactions that drive probiotic synthesis, like the famous Miller-Urey experiments, where simulated lightning and, by extension, UV radiation helped create amino acids. The CUVB could be a cosmic Goldilocks factor, its intensity quietly nudging some planets toward habitability while sterilizing others. Now zoom out to exoplanets. Imagine a world orbiting a quiet red dwarf star already exposed to brutal stellar flares. Add the relentless drizzle of the cosmic ultraviolet background, and its atmosphere might erode faster, stripped away molecule by molecule. Or consider a planet straddling the edge of its star's habitable zone, just warm enough for liquid water, but only if its atmospheric chemistry holds. There, the CUVB extra energy could tip the balance, either sparking protective ozone formation or shredding nascent greenhouse gases, turning a potential Eden into an icebox. The wild card is time. The CUVB wasn't constant over cosmic history. It surged during eras of rampant star formation and quasar activity. Planets forming in those violent epochs would have faced an ultraviolet onslaught far fiercer than today's background. Did early life in the universe have to evolve under relentless UV stress, developing radical adaptations like radiation-resistant DNA or subterranean biospheres just to survive? Or did the background's fluctuations create brief, precious windows where UV levels were just right for life to emerge, like tides receding to reveal fertile tidal pools? Astrobiologists are already piecing together the implications. Lab experiments show how varying UV intensities affect the stability of potential genetic molecules like RNA, while models of exoplanet atmospheres reveal how external UV sources alter climate dynamics. The James Webb Space Telescope's observations of distant planetary systems could provide real-world tests, especially around low-mass stars where the CUVB contribution might rival local starlight. Yet the most profound question remains unanswered. Is the cosmic ultraviolet background a silent partner in the universe's habitability or a capricious gatekeeper? Its influence might extend far beyond what we've imagined, not just shaping where life could arise, but when. In a cosmos where every photon tells a story, the CUVB could be one of life's oldest, etched in ultraviolet across the sky. Every story has an ending, even the universe's. Right now, the cosmic ultraviolet background hums faintly across the cosmos, but what happens as the universe stretches toward its distant future? Will this glow fade into silence or etch itself permanently into the fabric of space? The answer hinges on two titanic forces: the relentless expansion of the universe and the slow exhaustion of its light sources. Picture the scene billions of years from now. Galaxies pulled apart by dark energy's grip will recede until their light can no longer reach us. The stars within them will burn out one by one, leaving behind black holes and cooling embers. As the universe's star-forming factories shut down, so too will the primary engines of ultraviolet light. No more young, massive stars, no more quasars devouring matter in brilliant bursts. The CUVB current sources will dim like streetlights flickering off at dawn, their photons stretched by expansion into longer, redder wavelengths until they slip entirely out of the ultraviolet range. But the background's fate isn't just about fading. Some components might persist in ghostly forms. Take the radiation from reionization, the ultraviolet blast that cleared the cosmic fog. Those photons, already ancient, will continue redshifting, but their energy could imprint permanently on the intergalactic medium, leaving a fossilized signal akin to the cosmic microwave background. Future civilizations, if they exist, might detect this relic glow in entirely different wavelengths, a palimpsest of the universe's fiery adolescence. Then there's dark matter's potential role. If hypothetical particles like sterile neutrinos are indeed decaying into UV photons, their signal could endure long after stars vanish, fading only as the last dark matter reserves deplete. This would transform the CUVB into a cosmic hourglass, its gradual dimming marking the slow evaporation of the universe's invisible scaffolding, the most dramatic twist. Structure matters. As galaxies vanish over the horizon of visibility, the background's uniformity could shatter. Instead of a smooth glow, the CUVB might fracture into isolated patches, islands of ultraviolet light adrift in an ever-darkening sea, each representing the last pockets of star formation or exotic particle decay. Over unimaginable timescales, even these will blink out, leaving a universe so expanded and cold that not even ultraviolet whispers remain. Yet in that distant emptiness, the CUVB legacy might linger another way. Its photons, though redshifted beyond detection, will still carry information about the universe's first stars, its elemental makeup, even its potential multiversal echoes. In a sense, the cosmic ultraviolet background isn't just light, it's a message in a bottle cast across time. Whether anyone remains to read it is another mystery entirely. From hidden galaxies to the echoes of the first stars, the 25 mysteries of the cosmic ultraviolet background form a cosmic detective story with no easy answers. Each clue we've uncovered, whether it's the baffling temperature fluctuations, the unexplained polarization patterns, or the tantalizing hints of decaying dark matter, peels back another layer of the universe's grand puzzle. The CUVB isn't just a glow, it's a living archive holding secrets from the dawn of time to the far future, from the smallest particles to the vast web of galaxies. Think about the contradictions we've wrestled with. The missing sources problem defies logic. How can half the universe's ultraviolet light have no clear origin? The eerie anisotropies, where the background brightens and dims in ways that shouldn't align with visible matter, hint at forces we've yet to name. And then there's the whisper of population 3 stars, their ultraviolet ghosts possibly lingering in the background's spectral fingerprints, a relic of a time before galaxies even existed. Each mystery isn't just a gap in our knowledge, it's a doorway to new physics, new cosmic histories, even new understandings of how life itself might emerge across the cosmos. But here's the most thrilling part: this story isn't finished. Every observation, every new telescope, every daring theory brings us closer to rewriting the rules. Maybe the answer lies in ultra-faint dwarf galaxies waiting to be discovered. Maybe dark matter's invisible decay is the key, or perhaps, just perhaps, the CUVB is pointing us toward something even stranger, a multiverse, primordial black holes, or physics beyond Einstein's wildest dreams. So now it's your turn. Which mystery grabs you the most? Is it the photon under production crisis, where the universe seems to be creating light out of thin air? Or the cosmic web's faint ultraviolet glow, a map of the universe's hidden skeleton? Drop your thoughts in the comments. I'd love to hear which puzzle fascinates you and why. And if you're hungry for more cosmic deep dives, hit subscribe to join me as we unravel the next great mysteries of the universe. The cosmos is full of secrets, and together we're just getting started.